All right, so good morning, everyone. Welcome to the third São Paulo School on Gravitational Physics. My name is Rafael. I'm one of the organizers. So the dynamics of today's lecture is going to be, well, this is going to be an online lecture, so we expect everyone to keep their cameras shut and microphones shut while the duration of the lecture. If you have any questions regarding the contents of the lecture, please send it on the chat or raise your hand, and then I'll call you out so Agata can answer your question. And whenever I feel there's some space, I'll read the questions that have been sent on the chat. If you have any questions about the organization, please do send me a private message on the chat. Before anyone asks, the certificates will be sent after the school. We will be monitoring the attendance at the lecture. So if you want to get a certificate, you should show up to all of the lectures. All right. So without further ado, it is my pleasure to introduce the first mini course, which we'll be giving by Agata Grechko. So Agata did her undergrad in St. Petersburg University, her bachelor's in physics. Then she went on to a master's in the Moscow State University before joining us at the University of São Paulo here for her PhD. She has been working in celestial holography, so she's probably one of the best people to introduce everyone to this very exciting field of research. So, Agata, the floor is yours, and yeah, have a good lecture.
Thanks, Rafael. I need to say a couple of words about the course itself before proceeding to the lecture itself. So the course, even though it's introductory, it's advanced, right? So it means that you need some more or less advanced knowledge in topics of general relativity and quantum field theory. Even though the prerequisites was saying that you need to know general relativity, you need to be introduced into it, and you have to have enough knowledge in quantum field theory, there are still advanced topics inside of these advanced topics that are needed before we dive into celestial holography. Okay, so my first lecture, I will try to put us all on the same page and introduce asymptotically flat spacetimes and their symmetries, which is more or less advanced topic in general relativity. And second of all, I will introduce some basics of two-dimensional conformal field theory. Again, from the first lectures, do not expect a lot of strictness, a lot of derivations, a lot of deep calculus, because I will just mention the essential basics. So we will be able to set the holographic dictionary, and everybody will be able to really enjoy the beauty of the celestial holography itself. When we will move on the second lecture, hopefully, to the celestial holography topics, there, of course, I will perform computations, derivations that are specific for celestial holography and celestial amplitudes. And there we will be more precise, more lazy, more deep in the material. So yeah, I hope you guys will learn something new, or for people who already know asymptotical flatness and quantum conformal field theory, that's great. We just refresh the needed knowledge to move forward. My lecture will be more or less brief, but I prepared lecture notes that I will share on Slack channel, and also I will ask to put them on the website of the school right after this lecture. So, for example, in the evening, you can sit with a cup of coffee, reading the lectures that are more extended in the topics that I will mention today. There will also be different exercises for you guys to do, so you can get to know a little bit closer the topics that we will talk about. So yeah, that's it. And with this, let's move to my lecture. This picture here is not just attention-seeking picture. Sorry, I think I can hear someone. Maybe not. We will talk about it during the second lecture. And we will discuss what's going on in this picture and what will go on in a real world like ours. Okay, so lecture one. Lecture one. We will call it asymptotic symmetries and conformal field theory. Let's specify why do we need this? Why do we need these topics to discuss, and how do they arise in the question of celestial holography? Well, celestial holography, as it's following from the name, means that there is some holographic correspondence between some symmetries in the bulk of our spacetime and on the boundary of the spacetime. So basically, if we have some spacetime, four-dimensional, 4D symmetries in bulk, and there is a boundary of this spacetime. We will specify which exactly boundary it is, how it works, how can we parameterize it later, but now just in the conceptual level. So there is a boundary, right, of this spacetime. And here in the bulk, everything is described by general relativity, by the metric tensors, curvature, stuff like that. Things happen here, particles collide, scatter, and then the particles, they originate and they go to the bulk of our spacetime. And this, to the boundary of our spacetime. And this boundary is where the two-dimensional CFT will live. So what we will do, what is our plan, is to set correspondence between the symmetries of the bulk and the symmetry on the boundary. Great. Which exactly spacetimes we will consider? We will consider asymptotically flat spacetimes. What this is, let's define it. Definition, asymptotically flat. Asymptotically flat spacetime is a spacetime that, far from the beginning of our coordinates, looks more or less like a Minkowski spacetime. So all the specific constraints we will impose on the metric now, they just basically say us, okay, far away, the spacetime looks like Minkowski one. Right, for the noise. Asymptotically flat spacetime has metric tensor G mu nu that in far away from the beginning of coordinates looks like a Minkowski metric tensor plus some corrections, and these corrections should satisfy specific specific property that far away, first of all, itself, it vanishes in the infinity, in the spatial infinity, right? So when we write down the limit of this function h mu nu, it vanishes good enough, no less than 1 over r. Second of all, that its derivative also vanishes good enough, even better than the tensor itself. 1 over r squared, and sorry, here should be the derivative. And the second derivative vanishes even much more better. D rho, d some lambda, h mu nu, 1 over r squared. Here the r squared is just the spatial distance from the beginning of the coordinates, right? This is the definition of asymptotically flat spacetime. So as we just mentioned before, indeed, if we go far away from the beginning of coordinates, we see that asymptotically flat spacetime looks more or less like Minkowski, right? Because it's just some Minkowski background plus some corrections that are vanishing at infinity. Good. Now it will be important for us to remember the structure of Minkowski spacetime itself in infinity. With this purpose, we will remember the Penrose diagrams technique. So, for example, we start with the coordinate system where we have the radius, we have the time, and in Minkowski, yeah, let's say it's Minkowski spacetime. When we go far away to the future, so for example here, what happens is that we arrive to time like future infinity, right? We denote it as I plus. I plus is time like future infinity. Here t goes to infinity, r is some constant. And this is where massive particles with speed that travel with speed less than light, they end up there. Massive particles end up there. Okay, what we have next? Well, these massive particles, they originate from somewhere. From where? From the time like past infinity, which we denote small I minus. Time like past infinity. Here, time was minus infinity. R was a constant. Right? And massive particles originate from here. Okay, then we have spatial infinity, space-like infinity. I0, it's when the nothing goes there. It's just far away from the beginning of coordinate. Space-like infinity. R goes to infinity, time is constant. Okay, and then we need two more infinities, which will be of great importance in our story, namely the null infinities, the past null infinity that we denote scry minus, and the future null infinity that we denote scry plus. And this infinities is where the massless particles originates and where they end up. So scry plus minus is where massless particles originate and end up. For these two infinities, it's important that here we said t plus r goes to infinity, while t minus r is a constant. And here on the opposite, t minus r it goes to infinity, and t plus r stays a constant. This will be our advanced and retarded coordinates that we will use in the following. So if we do the conformal transformation of this map, do Penrose diagram, we will arrive to the following picture, where all the infinite points, they are now finite points at finite distances, and we can more clearly see the structure of the spacetime. Well, I will not tell a lot of things about Penrose diagrams. That's a very beautiful technique. What I will do is denote again where is the I plus, I minus, I zero, and here this part here is all of it is the future null infinity. Future null infinity and past null infinity. Okay, so this is how the Minkowski spacetime looks like at infinities. Very good to know that actually to study asymptotically flat spacetimes, on infinity, we can study the null infinities of Minkowski. So the null infinities of Minkowski is the same as null infinities of asymptotically flat spacetime. And this will be essential for our future analysis. So scry plus minus of Minkowski is equivalent to scry minus of asymptotically flat spacetime. Okay, great. And now we are interested in setting some coordinates, in finding the metric near our null infinities. How will they look like? Well, for example, it is possible to reduce the metric near scry plus in asymptotically flat spacetime. It's possible to put metric in the following form: dr squared minus du. I will give explanations about the notation as soon as I finish writing down this formula, okay? Minus du dr plus 2r squared gamma z bar dz bar This is, by the way, the metric of Minkowski spacetime so far. This is nothing else but just Minkowski. And this is an exercise for you to check. Exercise. And then we have our corrections and infinity. So first correction, 2 Bondi masses over R times du squared plus R times some tensor, shear tensor, what we will call later, dz squared plus its anti-holomorphic part, dz bar squared, and two more terms, which so far for our analysis, it will be enough to expand our metric up to this dz, du dz, and plus again the anti-homomorphic du dz bar. Okay, I need to again put it a little bit. Yeah, and then we have more and more corrections of the smaller and smaller powers of R. We can basically continue to whatever order we want, but for today, it's enough for us to see up to these terms, right? On the second lecture, no, actually on the third lecture, we will expand it a little bit more and learn a little bit more about our spacetime. But for now, we're okay. Now important to
Agata,
yes, me.
there's a question in the chat regarding I guess the last expression that you wrote. Gigan is asking, why do we have 3 identical indices in one monomial?
What in where do we have 3 identical indices?
I am not sure. Oh, the DZ, C subscript ZZ.
Because they are identical, because it's the let me firstly, explain the notations that I just wrote, and then we will see if your question still holds, right? So first of all, what is the U and all the Z and Z bar? U is our advanced, retarded coordinate, t minus r, just the normal time, just the normal radius, and z and z bar are just the stereographic coordinates on the sphere. Okay, so where there are only z and z bar together, it means it's a part of the sphere, it's spherical part of the metric. Here, phi and theta, they are just normal spherical coordinates, our usual ones. Okay, now answering your question, this is covariant derivative on a sphere. Okay, so it's just the covariant derivative on a sphere with respect to z. And this is just the part, like just the part of the metric that stays in the little in the component z bar. So if we write down the metric as a four component kind of thing. Here we will see the z bar part, sorry, z part, z bar, z bar z, and z bar. So this is just the this one's a 0 here. Oh no, this one is this the r squared gamma z bar, again r squared gamma z bar. This will be our shear tensors. And so here, this is just we take the covariant derivative on a sphere with respect to one of these coordinates on a sphere. It's just this. So this is Z.
I guess the question that he's trying to ask is whether or not this Z is contracting the Z in the DZ
No,
is
no, it's
contracting
not
with this.
contracting. It's
Yeah.
I'm writing down the metric in the components. So it's not contracted. If they were contracting, I would be writing something like this: dA, CA, B, AA, I would say, or AB, because for C it's only identical indices exist, and then DU, DZA. This would be the contraction. Yeah. This is just expanded form of contraction, so we can see more clearly what's going on in the components. All right?
Yeah, he
Okay.
thinks. He thinks you.
Yeah, okay. Good. So again, let's us look a little bit more clearly in details on this formula. First part is Minkowski metric here. Again, this gamma here is the identical metric on a sphere, just the identical metric on a sphere. And the MB here is Bondi mass aspect, so we call it. This way because in some spacetimes this can be connected to actual mass in the system. Bondi mass aspect. And this here is what we call the shear tensor. Basically, the CZZ bar, CZZ, CZZ bar, Bondi mass aspect, they encode data on the plus and minus, scribe plus and minus. So the data that we receive from null infinities or sent to null infinities is encoded in these parameters here. These parameters will be important for us, and yeah. Now looking at this form of the metric, which is the metric in the Bondi form, we call it. We are interested which transformations will preserve metric in such a form. And we will not perform analysis here that leads to vector fields generating I see a question, but I will answer a little bit later. So we will not perform all the analysis that leads to the vector fields generating this generating the symmetries of such metric, but we will write down the vector field itself. So if we write it down, for example, again, this metric can be written in completely analogous way near the past non-infinity. Okay, so the metric can be written using the advanced coordinate in this time, which will be v, and it will be completely analogous. In my lecture notes, I will write it down. Here, I will not spend time on it because just the same. And in the end, we will need only to understand only the form of such metric. What is the motivation for adding these terms? The motivation is that asymptotically flat spacetime is not Minkowski, but it's somewhat like Minkowski. So we need to add terms that vanish good enough when r goes to infinity. And this exactly are terms like this. And we cannot describe asymptotically flat spacetime by just Minkowski metric. We need to add something, but this something should decay very good at infinity. So this is the motivation. Okay, now let's write down the vector field generating symmetries of so-called Bondy-Metzner-Sachs symmetries, because it was back in 1962 when Bondy, Metzner-Sachs, and Vanderburg, they discovered that suddenly symmetries of spacetime described by this metric, it's not just Poincaré symmetries as they expected. This is something richer than Poincaré, and to see this, we can write this metric, this vector field. So near the future infinity, we see that the vector field is just the following: 1 over r d z bar f dz plus dz f dz bar plus dz dz f dr. I will not spend time on deriving it, but let me comment important things. Here, f is a function on a sphere that depends on the z and z bar. Okay, this function can be any function on a sphere. So vector field generating symmetry transformations of such metric has infinitely many parameters. This fz bar can be definitely completely anything. And on a sphere, on a two-dimensional sphere, right? But if we take, for example, if we consider fz bar being some constant, we will recover the translational symmetry in U, in our retarded time. If we consider f to be L equals 1 harmonics on a sphere, I remind you that, for example, for f equal for f that is sinus theta cosinus phi, right? That can be described in terms of holomorphic anti-holomorphic in terms of stereographic coordinates. This will recover us. We will recover translations in the x directions, x translations. Then, after taking f to be another harmonic on a sphere, we will recover the translations in coordinate y. And then if we will write down this version of z and z bar, we will recover translations in z. So these three particular examples of our f will give us just normal spatial translation invariance, right? Spatial translations. Meanwhile, the constant one will give us the translations in time. But all the other rich, humongous amount of f, they will give us something completely undescribable. And this set of infinite set of functions f we call super translations. F generates super translations. Okay. So what people discovered back in 1962 that asymptotically flat spacetime, its symmetries on the boundary is given by an infinite group, even though they expected it to be Poincaré, because, right, if it's kind of like Minkowski, it should be like Poincaré. But no, there is this interesting richness on the boundary. Okay, so if there is some kind of symmetry, then there are probably some charges that we can write down. But notice that when we were talking about our structure of Minkowski spacetime, we completely didn't specify how data on future null infinity is connected to the data on the past null infinity. So far, it's completely disconnected things. They are not, there is nothing connecting them together. And well, this is very important for us to impose matching conditions on these two null infinities. And to do so, we will write down the matching conditions for our Bonzi-Mass aspect, for our shear tensor, and it implies the matching conditions for the function f. So let's denote.
Agata,
Yes.
before you move on, there was a question in the chat a little bit before about the metric that you wrote down, the perturbed metric. So Marcus is asking, how do you guarantee that these perturbations are actually a solution to Einstein's equations?
Well, you just solve Einstein equations. You just substitute this in Einstein equations, which is a very long story, to be honest. And yeah, like about a year ago, I was doing this, but I will refer you to original. I will refer you to original. Uh, I will refer you to original article on BMS, or maybe to some more modern overviews of it, and then you will just order by order impose the Einstein equation. But again, you can check it, you can do it. I will not do it, and I will not check it here. Like, it's just a metric. You can just check if the Einstein equations are holding. The part of Einstein equations that give us the constraints, we use it a lot in this formalism. You can also see this in my lecture notes that I will post a little bit later. But for now, well, you can just believe me that Einstein equations works. Okay. Again, yeah, this is a completely a big story. I could give a mini course on just deriving this form of the metric, but I will not. And this is not what we will focus on, okay? Today and in the next lectures. So what we do is we want to consider processes again, right? That origin of the part of massless particles that originate somewhere on Scri minus and then go to Scri plus. And we need some initial conditions to solve such problem. Otherwise, we will not be able to perform any kind of analysis. So we, for example, will call the boundary of Scri minus is Scri minus is V goes to plus infinity, and there is some dependence on Z and Z bar. This is the boundary of our past null infinity. This is the boundary of future null infinity. So these two things here, they only depend on stereographical coordinates. It's basically spheres. Because the infinities itself, right, the scries, they are something like a cylinder, three-dimensional cylinder. And if we consider the, for example, Scri plus, we consider the limit of u goes to infinity, we will recover some kind of sphere. This is actually a sphere, okay, two-dimensional sphere. And these two spheres S2 is where our celestial things will be going on. Okay, so this is where our two-dimensional CFT will live and have some interesting properties. So these things here, they are important for us. And the boundary conditions that we impose are, matching conditions that we impose, I mean, they are boundary in some sense. Matching conditions that we impose, they are also defined on these two spheres. So if we write down our shear tensor, parameterize it in the following way, for example, on the Scri class, it's 2D. Z bar, right? No, just Z squared. And this is some function on the sphere, some function C. Then we impose some matching conditions. Matching conditions C on of Z bar on scry plus minus equals to C, Z, and Z bar on scry minus plus. Actually, the version of shear tensor in the past null infinity we can, for clarity, call D, right? It will live on the past null infinity in the upper boundary of it. Now we just, that's a lot of D's here, plus minus. So basically we can write this way to differentiate them somehow. Anyway, they are now the same, so we identify them, and we also identify the Bondi masses on scry plus and scry minus. Z bar on scry minus plus. Okay, this is how we glue together the asymptotic data on scry minus and scry plus. This will imply that for our functions, our functions are also f are also fixed on these boundaries, right? So these functions are also fixed. And now what is important here is to notice that since there is symmetry, there are charges, and these charges are actually conserving because of our matching conditions. So for example, the charge on scry plus connected to the transformation f is 1/4 pg integral over the two-dimensional sphere, right? The boundary, where z times metric, our transformation, and Bondi mass. And the same formula for the charge on the upper boundary of scry minus. The same formula. And as we can see, with our matching conditions, these two charges coincide. So these two charges are the same thanks to matching condition. Yeah. Okay. The important thing here was for me to introduce the scry I plus minus, scry I minus plus, to explain to you that this is where our two-dimensional CFT will inhabit, and also for you to understand what is asymptotically flat spacetime. I think we are finished with asymptotically flat spacetimes, and we should go towards the conformal field theory. So I refer you to look through my notes that I will lecture note for the first lecture that I will send you later after the lecture. And also maybe read, remember some general relativity books for people who want to see the derivation of the Bondi metric. Also, I refer to the original paper. So yeah, that's it for now for about asymptotically flat spacetimes. All good? Okay. Let's move to CFT. So thanks. We just understood that where the two-dimensional conformal field theory will be, where we will consider it. And now let us remember or introduce what is conformal field theory about. So we start with CFT, right? We start with the definition of what conformal transformation is. Conformal transformation. What is a conformal transformation? Conformal transformation is a coordinate transformation when metric transforms up to some scaling. So if we have a coordinate transform from x to x prime, it will be called conformal if metric transforms in the following form. Now I will put down the indices after I write. Mu here G rho lambda of x. Oh, sorry, I'm a little bit Russian here. It's just the scaling dimension, scaling factor, some scaling function times the metric before transformation. I will add some recommendations with the lecture notes, but let's talk about it in the end of the lecture, all right? Okay, so this is what is conformal transformation in general. Now we will be only interested in the conformal symmetry and conformal transformations in 2 dimensions, since our celestial sphere. Yeah, I'm not sure if I told you, but this is what is called celestial sphere. Celestial spheres. So this will be only interesting for us in 2 dimensions, and in 2 dimensions we can start with the metric on a plane, right? In 2 dimensions we start with the coordinates z0 and z1 on a plane. The metric is flat in the beginning, and then we do a transformation, change of coordinates from z to w. Okay. We know how the metric tensor transforms, right? Just from, I don't know, usually general relativity course. So our metric, 2-dimensional metric tensor in the new coordinates, it will be the old coordinates and old metric tensor of beta of z. Here is alpha, here is beta, here is mu, here is nu. When we combine these two, these two equations, since the original metric was flat, right? So this one was something like 1, 0, 0, 1. When we transform it, it will conformally. It will be something like lambda 0, 0, lambda. So we will have in the transformed metric, if the transformation is conformal, we will have only the elements on the diagonal. So only the element 1, 1, prime 1, 1, and the element prime 2, 2. They will be the same because the scaling function is the same for them both. And this equation on them will look like this if we expand the transformation rule. So dz0 squared plus dv0 dz1 squared equals to dv1 dz0 squared plus dv1 dz1 squared. This is our first important constraint. And this is our second important constraint. We see that both component 1, 0 here and 0, 1 here, they are equal and they are equal to 0. And so therefore we can just write down the following condition that the dv dz0 dv1 dz0 plus dv, I will call the w sometimes v, sometimes omega. Please do not be confused by this. It's all the time, it will be w. So dw0, dw1, dw0, dw1 over dz1, dz1 equals to 0. We obtain these two equations, and lucky we, to solve these equations with respect to, yes, this should be G00 0 and 1, 1. You are totally right. Thank you very much. Yeah, so to obtain, to satisfy this equation, we can solve it with respect to these 4 variables. And when we solve it, we obtain the Cauchy-Riemann conditions for holomorphic or anti-holomorphic function. So if we solve it, we obtain the Cauchy-Riemann conditions for, let's restrict ourselves to holomorphic functions and for holomorphic functions. So these conditions are what? These conditions are dv0 dz1 equals to dw1 dz0 and dw0 over d z0 is minus dw1 over dz1. All right. We obtained the Cauchy-Riemann conditions. This means from now on, we can and will and should use the coordinates z and z bar. Holomorphic, non-holomorphic coordinates. We go to z, that is just z0 plus I z1, and z bar, which is z0 minus I z1. And the differentials also, we will denote it just d. Okay, this will be our differential with respect to holomorphic coordinate. d1 minus d0 minus I d1. d0 minus I d1. And the differential, we will denote it d with bar d, is given by this. Okay, great. Important note here, actually very important. Note that here we were living on a real plane, right? Z and Z bar, Z and Z0 and Z1 were some real coordinates on a plane, and they were independent. Independent R2 coordinates. And then we go to Z and Z bar that in principle should be constrained. They should not be independent, right? Because they should be just related by complex conjugation. But in our analysis, we will say, no, they are actually independent. They are two independent complex variables. And then when we go to some physical space, when we consider physical things, we impose this condition here. So is it true? Actually, no, because we will consider them independent complex coordinates. We take Z and Z bar as independent complex coordinates. Okay. That is about the coordinates in our two-dimensional conformal field theory. Now, what about the transformations itself? Can we classify them somehow? Yes. There exist global conformal transformations. And global conformal transformations are transformations that are holomorphic everywhere on the whole Riemannian sphere, right? And by Riemannian sphere, I mean the same. It will be identified with our celestial sphere. So whatever sphere we are living at, global conformal transformations are holomorphic everywhere because Cauchy-Riemann conditions are only valid in some area, in some point, right? In some region. So in general, there can be holomorphic in some region function that is not holomorphic everywhere. This is why we specifically should talk about global conformal transformations that are holomorphic everywhere. These global conformal transformations, they are holomorphic everywhere, and they can be given in the form of Möbius transformations or projective transformations. They are written down as following. TZ plus D. Here AD minus BC equals 1, and A, B, C, D are all some complex numbers. What is beautiful about them is that they are isomorphic to the group of matrices. For example, it can be written down as a matrix A, B, C, D with determinant equals 1, right? This condition just translates to the determinant 1. And this is nothing else but SL special linear to C group, right? It's special because determinant 1, linear because matrices, and dimension 2, and it's on the field of complex numbers. So the ABCD are complex numbers. So it's SL to C group. And our transformations, for example, superposition of two global conformal transformations can be written as a composition of two matrices. So it will be some A2, A1, some third matrix. So these global conformal transformations, they form a group, right? The superposition of two transformations give the third one transformation. And this group is a cell to C. That's a very important name in our whole story. I will put it in very big letters because it's very important. These global conformal transformations. And we will return to it many times. Okay, now global is good, but most of the transformations, right, there is a lot of local transformations. How we classify them? How do they act? What is their algebra? Let's talk about conformal generators in general. So in general, our conformal transformation, infinitesimal conformal transformation can be written down as the following epsilon of z, where epsilon can be performed as a Laurent expansion in z, n plus 1. This is just some coefficients, and the powers of z go from minus infinity to plus infinity. So you can see that, for example, around 0, it has a lot of poles, right? So it's not global in general. And if we expand, for example, if we take some field, let's say scalar, because it's easy and nice, scalar field phi, living on the plane, and perform an infinitesimal transformation infinitesimal transformation on this field, which will be like transformed phi over transformed variables minus the initial phi of the transformed variables. If we expand it in the powers of epsilon and then tied it all up together, it will give us the following expression: Cn ln plus Cn with bars, anti-holomorphic part, of phi z z bar. Here, this little else is our generators of conformal algebra. Generators of conformal algebra, and they are written in the following form. It just from the expanding this expansion here. It's nothing really difficult. I'm just skipping here because it's some technical details, and important for us is to see what they are, not how they are obtained. So this is our ln bar analogous, and this is our generators of local conformal algebra. They obey commutation relations. Ln with some ln is m, no, n minus n, ln plus n. The same with the barred ones, n minus n, l bar, m plus some n, and bar with not bar is 0. So this algebra is called Witt algebra. Actually, 2 copies of Witt algebra, right? Because there is they are independent, the holomorphic and anti-holomorphic parts. So altogether, they are just 2 copies of Witt algebra. Witt times Witt algebra. This is basically the definition of our Witt algebra. And isn't it supposed to be PSL? I think PSL is also factorized by, if I'm not wrong, it's factorized by the integer numbers, and I think A, B, and C should also be, what Nick just wrote. I think that would be PSL. Okay. Now important notice again, because in most of the celestial holography literature, and we also will do that, this is called not Witt, but Virasoro algebra. People know, probably some people know that Virasoro algebra is Witt algebra with central expansions, so some additional terms that do not appear here. Well, we will just call it mostly Virasoro algebra, even though it's a Witt algebra, and we will not be very strict about it. Here important also to notice that if we take a subalgebra of L minus 1, L0, L1, this will form us our SL2C algebra. So the global conformal transformations. global conformal transformations. Right? So for example, the L-1 will correspond to translations on the plane. L0 will be scale transformations and rotations. And L1 will be special conformal transformations, which in the case of two-dimensional CFT is inversion of within zero with infinity, right? Inversion, then translation, then inversion again. This is what special conformal transformation is. Okay, so far so good. I hope you liked the conformal algebra. And now also another central notion in our story is primary fields, which are very important in conformal field theory. Primary fields. We in CFT we need a we have the generators of our algebra, and we need a space of states and fields of local fields, and these fields should be annihilated by lowering operators, lowering generators of conformal algebra, and they should obey a certain transformation rule. So to understand what is a primary field, let's firstly say that we define holomorphic conformal dimension of a field, holomorphic conformal dimension H of a field is a sum of scaling dimension, which will and the spin. And anti-holomorphic is just h bar, okay, of the difference. So now we can finally define what a primary field is. A primary field is a field F, phi, I think it's better to say phi, of z bar that under a conformal map, right? Here is important that the map should be conformal. From z to omega z and z bar. Yeah, omega w, yeah, w bar of z bar transforms as following. So the new field transformed one of w bar is the derivatives of the new coordinates over the old coordinates in the power of conformal dimension. Minus h bar times z bar. This is actually, it's a quasi-primary field. Quasi-primary field. But as with the Virasoro and with algebra, the same story will continue in quasi-primary and quasi-primaries and primary fields. Because quasi-primary field can transform as following, as I just wrote, under only global transformations. Meanwhile, for a field to be primary prime, it should transform this way under any conformal transformation. So most of the times we will just call it primary. Whatever transforms under SL to C is primary. Whatever transforms under any other conformal transformation, like local conformal transformations, is also primary. We will not pay a lot of attention to this. But actually, funny part is that we start with calling quasi-primary fields primaries, but actually we will arrive to the fact that they are truly primary fields. But this is the story for second or third lecture. Okay. We have our fields, we have the notion of fields being primary, and now we are almost here. We almost finished our little dictionary, little conformal dictionary. We just need to couple of more notions. Let's continue with correlation functions. Since we have fields, right, and it's field theory, we will have some correlation function. Correlation functions are very interested in CFT because conformal field theory will restrict them to a specific form. For example, two-point function of two fields, Z1 bar, F2, Phi2, Z2, Z2 bar is fixed by conformal invariance either to be the following thing, Z1, 2, 2H, Z1, 2, 2H bar. Here, Z1, for example, Zij is Zi minus Zj, and the barred one is just for shortness of notations, okay? So it's either two-point function into the CFT is either this expression here, if conformal weights coincide, H1 bar, H2 bar, H, or it's zero otherwise. In my lecture notes that I will send you guys, there's a little bit more detailed derivation of how this happens and why this happens. For now, let's just do a little overview of this property. Okay, two-point function is not the only correlation function that is actually fixed by conformal invariance. There is also a three-point function. I will not write down the dependence on Z1, Z2, Z3, okay? We'll just write the correlator of three fields. And this thing here has the following form. It's some constant again. Yeah, here is also some constant, C1, 2. Here also constant times the following ratios. Z1, 2 in the power of H1 plus H2 minus H3 times Z2, 3 H2 plus H3 minus H1 times Z3, 1 or 1, 3, 3, 1, I think, 1, 3 times in the power of 1 plus H3 minus H2 and times the anti-holomorphic part. So there is also the same thing with with the anti-holomorphic variables. Okay, I will not write it down, but this is how our 3-point function should look like in two-dimensional CFT. However, that's all that we can get from the conformal invariance. We cannot live on it freely further, because at the moment of 4-point function, we already don't have a fixed form given fixed by only conformal invariance. Because 4-point function can be any function depending on cross ratios. I will comment soon what is a cross ratio. Times the old product of our the ij, the ij bar. Okay, this eta here is a cross ratio that is z12, z34, z13, z24, and it's conjugated. So 4-point function can be anything depending on this cross ratio times our factorized product. Well, but it's still good. It's still good because when we will, since we will consider CFT on celestial sphere, and we will calculate the correlation functions, and we can compare them with the correlation function that we expect to see in CFT. So far, so good. Okay, and we're almost ending. I hope you're not very tired. I promise that the next lectures, they will be a little bit more chill. There will be less dense material, but let me just finish with just two definitions in our CFT. One of them will be word identities. For correlation functions. So there is conformal symmetry, right? There is symmetry and there are correlation functions. Of course, what we want to do is to write down some word identities on the correlation functions. And when we do so, we obtain the following rule, that the variation under the conformal transformations of some correlation function looks like this. This is the infinitesimal generator of our, actually we can write it as z, why use the w? As infinitesimal generators plus something depending on the conformal weight of the fields, weights of the fields. This is the conformal word identity. At the place of x, you can just substitute any correlation function, right? Any point correlation function. And then see how it transforms under our conformal transformations. This word identity has identical formulation in terms of tensor, stress energy tensor. So if we insert the stress energy tensor inside the correlation function, we will get the a familiar expansion. Familiar, I mean similar to the one that we see here. We will see the pole structure of the correlation function, plus some regular terms in z minus w e, which are not interesting for us. Why they are not interesting is another story, but important part for us will be the singular part. Okay, singular part of things, the singularities. And here, yeah, this stress energy tensor is connected to the familiar one through this relation. Okay. So this is just the component of stress energy tensor that we insert inside the correlation function. Interesting to see how the global word identities look like. I think it's important for us. So, for example, if we substitute here our global subalgebra L0 and L plus minus, right? If we substitute them here, and what we will obtain is three relations on correlation functions, because under the global conformal transformations, correlation functions are the variation must vanish for global conformal transformations. This is what we will obtain. dv wi plus hi next, and the third one connected with the special conformal transformations. hi x. This is the global word identities. Someday, maybe tomorrow, maybe the day after tomorrow, we will need it. Global word identities. Great. And the last thing that I wanted to talk about that is very essential in conformal field theory is operator product expansion, or shortly OPE, operator product expansion. Because what is this? When our points inside the correlation function starts to coincide, when they approach each other, we start having singularities in the correlation functions. So what we want from our toolbox of CFT is to have some possibility to represent these singularities in more or less structurized way. So operator product expansion lets us represent the singularities as something regular and well defined when two positions coincide, go close to each other, times something possibly divergent as z goes to w. So we define our OPE of two fields as of two fields, yeah, let's say A dependent on Z and B dependent on W. A over Z times B over V W of W as infinite sum of terms. Let me write it down, and I will give a few comments. So here you can see that, for example, it has only Finnish amount of terms that are singular, right? As Z approaches W, and the infinite amount of regular terms, right? When n goes to plus infinity, it just gives us some terms like z minus v in the positive power. And as I mentioned, we don't really care about the regular part in conformal field theory. So yeah, that's how we define operator product expansion. And here, this is just some new operator that is AB is a new operator, is a field that is non-singular. Non-singular as Z goes to W. So yeah, that's all what I wanted to say about CFT and asymptotical flatness for now, for today. And of course, conformal field theory is much richer than just these 3 pages, 2 pages, 1 to 3 pages. It's very interesting science, and I encourage you all to look into it, to read some books or maybe see some course in it. And because it has implications in most of the fields in theoretical physics, in string theory, in ADS-CFT, right? And I encourage you all to somehow learn it if you haven't done it yet. But for us, it will be enough to have this reduced amount of tools to see the ideas and to set the dictionary, the holographic dictionary for celestial holography. So all these things that I mentioned in the second part of the lecture, all the CFT creatures, they will live on the two-dimensional celestial sphere from the first part of the lecture, at the scry plus minus, where is it? Here, scry plus minus celestial spheres. And tomorrow we will finally set the dictionary between the bulk and the boundary and see which properties it has. During the third lecture, we will describe the symmetries of such a spacetime. So thank you all for your attention. If you have any questions, I can try to answer them. And what else? Yeah, maybe sit down today with the notes that I will send and try to reread them all just to refresh these things.